section on electrophilic aromatic substitution too. It's really powerful chemistry. It's, you know, pretty enjoyable. All right, so now what we're doing is we're moving on to the whole section on, if you can see here, nucleophilic and electrophilic aromatic substitution. Now, most of what we cover in the chapter is going to be electrophilic aromatic substitution. But remember, we did talk about SNAR reactions, and we also talked about elimination addition reactions. So those are important as well. Now, if we go down here, the first one I chose was question number 1. You really have to know your substituents. Which one is an activating versus deactivating groups. Okay, so if I look at the 3 groups that are here, well, the carboxylate is going to be deactivating. So this is deactivating. Why is that? It's pulling electron density away from the ring, right? The same thing with the second one where you have the ammonium ion. Well, that's got a positive charge. I mean, that's mega hungry for electrons. So it's pulling electrons towards itself. So this is highly deactivating. And then the hydroxide, or the hydroxyl group, well, it's electron withdrawing because of induction, but it's electron donating via resonance. And resonance will always dominate over induction. And so the hydroxyl group is actually activating. So we'll put here activating, okay? It's actually a strong activator in this case. And so the 2 deactivating groups are going to be number 1 and 2. Is that one of the answers? Yes, it is, okay? B is 1 and 2 only. So make sure you review the table of activating versus deactivating groups, and you know which one is strong, moderate, and weak, and you know the halogens, which are an exception. Okay, let's try number 4. It just says here, how would you do this transformation? So you have toluene to start with, and then you want to make para-bromotoluene. Well, you guys know that a methyl group is a weak activator, so weak activator, which means that it is a para-director. So it's technically an ortho-para-director, so it can activate to both positions. But in this case, you see that they only give you 1 reaction for each one of them. So you just have to choose the best answer. Okay, so how do we do a bromination on an aromatic ring? Well, it isn't with bromine and carbon tet. It isn't with bromine and UV light. We use that for free radical reactions. This is not. Right, Erica? Exactly. We're going to use bromine mixed with iron 3 bromide. That basically creates a bromine with a positive charge in essence, okay? And so now your ring is going to be able to attack like this. You make the sigma complex, you do the proton transfer, and you restore aromaticity. Awesome, awesome. Let's try number 5. It just says, which one of these sets of reagents would make propylbenzene? So if somebody says, I'm going to write you a big check. All you've got to do is make me some propylbenzene. What are you going to do with it? I don't know. Anyhow, so if you make some propylbenzene, you get some money. Okay, so let's take a look at A. A, we're doing this is a Friedel-Crafts acylation, okay, with the acid chloride. And then this reaction here, if you remember, this is called the Clemenson reduction. And so in that case, at first you're going to make, come on, draw a 6-membered ring, you. Okay, at first you're going to make the ketone, but then after you do the Clemenson reaction, just bear with me, I'll find my place again. Where was I? I was down. Nope, I'm past that. Son of a gun. Oh, Mr. Dion, somebody's trying to tell me something, I think. Where am I, or where was I? There I am. Okay, good. So, no, that's not it. It was this one here. So, in the first step, as I was saying, we make the ketone, right? But then, as I was trying to say, when you do the Clemenson reduction, you burn off the carbonyl. So yes, A is going to work. So A had better be the answer. Let's just look at the other ones. The next one, you have 1-chloropropane in aluminum trichloride. That's a Friedel-Crafts alkylation. But remember, this is going to mostly rearrange. So you're actually going to end up with a mixture of isopropylbenzene and propylbenzene. So you'll end up with both of those. So that's not great because that's a mixture. So we'll cross that off. The next one, you would do a bromination in the first step, and then you would treat it with propyl magnesium bromide. I don't even know what the heck that would even do. The next one is you'd make chlorobenzene, and then you would treat it with this alkene and Friedel-Crafts. That's not going to do anything either. Okay, so A is the only one that is only going to make propylbenzene. And as a matter of fact, in B, the major product in that case would be this. This would be the major product. You get mostly the rearrangement there. Okay, so that's a little bit of Friedel-Crafts and some Clemenson. So make sure you review Friedel-Crafts and Clemenson reactions. Ooh, question number 6 is a good one. It says you make a nitronium ion. Sounds like fun. So let's say you made this nitronium ion and it's just hanging out and it's just waiting for a nucleophilic attack. Okay, this is highly reactive. And then it says, well, which position is going to attack the nitronium first? Okay, would it be A, B, C, or D? Well, if we look at each one of these substituents, if we look at the acyl group here, we know that this is a moderate deactivator. Okay, and then if we look at the methyl group, we know that this is a weak activator. So who's going to win? Well, the activator is going to win over the deactivator. So we'll just kind of cross this guy out and say, well, it's going to be based off of the weak deactivator. Now, if we just look at this ring, if we just focus on the ring with C and D on it, well, we can also take this entire group and say, well, this is an aromatic ring attached to this position. So this carbon here that I'm putting, maybe I'll use green. This carbon here is just an sp2 hybridized carbon. And so that means that this whole group is also going to be a weak activator. So this whole damn thing is going to be a weak activator, and it's going to be an ortho pair director. So that means that C and D are both open to substitution. So now we have to go with our wits. Which one of these positions do you think the nitronium is going to add to preferentially? Would it be the C position or D position? Well, if both groups attach to these positions, and I'm talking about this position and this position, okay? If they're both weak activators, I would go by sterics. And this group here is much bigger than this little methyl group down here. And so the position that's preferentially going to be nitrated is going to be position D, okay? So it's not only based on the activating group or the type of group attached to the aromatic ring, it's also based on sterics, right? The size of the group that is attached to the ring. Let's see here. Question 10 was the next one I had. Let's do question number 7 because it's one, I didn't have this in the list, but this is one that is important for you to know. And it's one of those things that surprises students sometimes. You know, students will ask me questions on the homework like, I thought you said this wasn't possible or something, but it's because they tend to forget this one little reaction that we went over, okay? It says, which description is most applicable to the mechanism of this reaction? So we have, what would you call this compound? I don't know, you call it chlorobenzene, so you'd call it 2,4-dinitro-chlorobenzene. Then you treat it with sodium hydroxide, and now you get a phenol. So you get 2,4-dinitrophenol. How does this reaction take place? In A, it says it takes place in 1 step, no ionic intermediates. Takes place in 2 steps, elimination, then addition. Takes place in 2 steps, addition, then elimination. Takes place in 3 steps and involves a carbocation intermediate. Well, this is definitely not a 1-step process, so I wouldn't say that, okay? Doesn't take place in 3 steps that I can think of. What's going to happen is we're going to add the hydroxide, right? The hydroxide is going to come in as a nucleophile like this, okay? And then we're going to form an intermediate, and I can't draw all the resonance forms in here. And then you're going to end up losing the chloride in the 2nd step. So elimination, I'll just circle here, elimination, come on, of Cl minus, like that, okay? So does anybody remember what type of reaction this one is? And it's not a trick question. Does anybody remember the name of this reaction? It is important. It will probably show up in your final exam, okay? If you don't, this is an SNAR reaction, okay? So if you remember, the requirements for an SNAR was that you have a good leaving group, right? Like the conjugate base of a strong acid, like a chloride, bromide, iodide, that you have a good nucleophile, like a hydroxide, and that you have a strong electron withdrawing group either in the ortho position or the para position. And here you see we have both, okay? So you do a nucleophilic attack, and then you lose the chloride in your SNAR. So let's take a look at question number 10 then, okay? If I take a look at question number 10, it says, which aryl chloride is going to react the fastest with sodium hydroxide? Well, an aryl chloride is going to react with sodium hydroxide. I mean, if you tried to react this, you would need extreme heat to do that, and you would do an elimination addition. Here you have a good leaving group. You have strong electron withdrawing groups, but they're not in the right position, right? These are in the 3 and 5 position. Here, this one is okay because the nitro group is in the 4 position, but look here, we've got 2 and 4. So this one is the one that is going to be most set up for the SNAR reaction. You have got a good leaving group. You have got a good nucleophile. You have got 2 strongly electron withdrawing groups in the 2 and 4 position. They're ortho and para to the leaving group. And so again, this is going to be an SNAR reaction. Let's continue on in the SNAR vein. And I'm kind of giving it away here. But this is a question, I've seen this show up on the final exam a couple of times, where it says, okay, you've got this aromatic compound. You're going to treat it with sodium methoxide, right? You know that sodium methoxide is a good nucleophile. But where is it going to attack? Is it going to attack at this position, or is it going to attack at this position? Can anybody tell me which arrow is correct? Would my red arrow be right, or my blue arrow be right? Because only one of them is right. One of them is wrong. Did anybody answer that based on what we said about SNAR? It's going to be the red arrow that's going to be the right one, okay? Remember, you've got to have a good nucleophile, a good leaving group, and the leaving group has to have the electron withdrawing groups in the ortho and para position, right? If you choose this one here, this one's wrong because these 2 nitros are meta to that leaving group, okay? The nitros have to be ortho and or para to the leaving group. So that is where we're going to have our SNAR. So if you look at the 4 answers, the one where you replace the chlorine with the methoxy is this one right here. And there you have it. Hot dog, we have a wiener. Okay, let's try number, so we did 11. Let's try 13. Another one I had picked out. Oh, I hate these ones. Which sequence of reactions is expected to give 3-nitrobenzoic acid? So let's say you wanted to make this compound. I'll just walk through them verbally here. So the first one, you've got a nitro group on it. Then you do a Friedel-Crafts alkylation. That would put a methyl group in the meta position. Then you do an oxidation with a Jones, okay? And that one, yeah, and that would oxidize to give you the carboxylic acid. So that one is reasonable, I would say. But I would say that this reaction isn't going to work really well because you have a strong electron withdrawing group. So I would put a question mark by that. That's not going to work very well. Whereas if we look at B, in the first step, we oxidize this to the carboxylic acid. Okay, that's after the first step. So the OH. Okay, so we have the carboxylic acid. Well, remember, the carboxyl group is only a moderate deactivator. And so it's also a meta director. And so the next step, you're doing the nitration. So this one looks like it's going to work too, okay? And it's going to be better than A because in A, Friedel-Crafts with a strong electron withdrawing group is just not a good option, okay? So far, B looks the best. Then you go to C. A methyl group is an ortho-para director, and then they're saying you do a nitration. So that would put the nitro here, and then you would oxidize this. Well, that would give you para-nitrobenzoic acid. And this one here, this is not even right because this is diazotization conditions, okay? This is for a Sandmeyer reaction. So this is not right at all. So the answer in this case is going to be B. First, we make the carboxylic acid, which only is a moderate deactivator, and then we do a nitration reaction. Number 14, what's the major product of this reaction? So we have, what would you call this? This is called phenylbenzoate. You're doing a bromination, so where's the bromine going to go? Okay, we have this position. So let me just use my highlighter. Para over here, meta over here, and meta over here. Okay, so none of them would be ortho because it's too sterically hindered. So we just look at the two groups that are attached, okay? Here you have an oxygen directly attached. An oxygen is going to be electron withdrawing by induction, but it's going to be electron donating via resonance, right? So this is going to be a moderate, activator. Whereas here on the other side, you have a carbonyl, right? And so that's going to be a moderate deactivator. So that means the site that's going to be most activated is going to be this site down here. And so the correct answer must be B. You're going to get parabromination where you have the moderate activator, not a deactivator. All right.